we're very happy to come to you from Northeastern University at our school. So Yizhi got a PhD from University of Illinois in 70. He was subsequently postdoctoral fellow at Princeton University, and Yizhi has wide-ranging interests from topological basis matter, non-equilibrium systems. Most recently, he has been interested in open quantum systems and the effects of noises. So yeah, today she's going to tell us about the steady state in open systems from holographic. Let's welcome Yizhi.
For the introduction, and thank everyone for this. I'm Yizhi from Northeastern University, and today I will talk about how to move from and go to steady state in open quantum system from a holographic nature. So to begin with, let me acknowledge my collaborator, which made everything happen. This work is mainly based on holographic that was in collaboration with Sarah from Princeton University, Peter from Perimeter Research to Maryland, and also Neil from MIT, who provide a lot of help in ISO-TNS setup. So since this is a Q-form, I think everyone comes from this. And when we do quantum physics in our undergraduate level text, one of the unique features in quantum physics is topological. So in the recent years, the preparation of quantum states that has large entanglement of topological features have been a central goal for quantum simulators and the processors. These type of wave functions could be used as a useful resource for some quantum information tasks like measurement-based quantum computing or error functions. And in the past decade, there have been different proposals being explored in how to build a programmable and a scalable device in various quantum optical atoms, nuclear atoms, and superconducting qubits. So imagine now we can build a many-body wave function that has some type of exotic entanglement. However, this wave function would inevitably interact with the environment in raw freedom. They get entangled with the environment. And we usually assume that the qubits from the environment in raw freedom are not controllable, also not acceptable. So the most thing I can do is just trace out all of the qubits from the environment and eventually get a reduced density matrix that describes the system of matrices. This process is known as decoherence, where it drives a Q state, a Q wave function, to a mixed state ensemble. And in our quantum mechanics textbook, qualitative descriptions of decoherence can be characterized in terms of quantum channels. So imagine I have a system of interest where I just abbreviate a single qubit, but you can imagine that this is something like a D-dimensional system. And I also have some ancillary raw freedom coming from the environment, which have the same dimension. And decoherence is I have some interaction between the system and ancillary, and this process can be characterized by a unitary circuit that entangles the qubits from the system with the ancillary. And because I assume that it considers qubits from the environment are not controllable, and I have no information about them, so I trace them out and eventually get a reduced density matrix that describes the system. So such kind of unitary operation that entangle the system and ancillary, and eventually trace out the ancillary, can be characterized in terms of a cross operator that act on the cap and bra space simultaneously for the density matrix. And this type of quantum channel would trigger decoherence and drives a Q state, a wave function, into a mixed state ensemble. And in addition, if we want to characterize such kind of decoherence process in a continuous time version, then just end up with the Lindblad master equation. So in terms of decoherence, there are two scenarios that are of particular interest in the recent years. The first scenario is finite time decoherence. So I assume that the wave function I initialize only interact with the environment for some finite amount of times. And a question on the agenda is, under such kind of finite time decoherence, does the original code still retain its logic information? And the other type of limit is what I want to describe today is I assume that I just let the coherence happen for infinite amount of time, that the Lindblad master equation appear for infinite amount of time and look into the steady state of the repeated quantum channel or Lindblad master equation. The question I can ask is, how do we characterize such type of steady state under a repeated quantum channel or infinite time Lindblad equation? And how can I fabricate and find interesting quantum channel that can give rise to some highly non-trivial steady state, albeit it's still a state density matrix? So in order to tackle this problem, what I want to introduce is a useful duality framework called the channel circuit duality. So first, let's look into quantum channel or repeated quantum channel. So this is a diagrammatic representation of the repeated quantum channel, where my system of interest that can be a d-dimensional Hilbert space is denoted as a red cube. Indeed, it represents a d-dimensional Hilbert space. And for a finite depth quantum channel, what I need is I just need to have a unitary gate that entangle the system with something from the environment that was initialized as a product state. Entangle them and trace out the ancillary. This is one depth of quantum channel. And I can repeat this quantum channel for infinite amount of time. So for the second step, I have a new ancillary and let it entangle with the system and trace out the ancillary and repeat. And if I repeat this quantum channel infinite amount of time, finally, I will get a steady state of the repeated quantum channel. So this is just a diagrammatic representation of what is repeated quantum channel or what is infinite time Lindblad equation. But in the meantime, this diagram also corresponds to a sequential circuit. So in the first step of the quantum channel, if I don't trace out the ancillary, but I still retain this, then I have a system qubit and ancillary, and I add a local unitary gate that entangles. In my second steps of the quantum channel, I have some new ancillary involved that I let it entangle with the system. And here, I choose a special geometry that I place the system, which is a d-dimensional Hilbert space here, and the first ancillary and second ancillary are spatially extended, say along the y direction or along the x direction. This is a two-depth quantum channel. And if I repeat in each step, I have a new d-dimensional Hilbert space, which is the ancillary wrong freedom. I add some unitary gate that entangle the system ancillary, and then repeat to the next process. During this whole process, if I do not trace out the ancillary, and assume I still have them, then this is nothing but a sequential circuit that generates a wave function in higher dimension. If I assume that the system together with the ancillary in each step are spatially separate along the y or x direction. So this is indeed sequential circuit. And now if I want to trace out the ancillary, because this is a repeated quantum channel, this is a sequential circuit. For the first ancillary, after the first step of unitary, I have an output state and it does not change after this step. So if I trace out the ancillary after this step versus trace out the ancillary at the very end, it doesn't change because after this step, after t for 1, the first ancillary raw freedom does not change at all. So in principle, if I get a wave function in higher dimension that is generated by sequential circuit, and I trace out all of the qubit raw freedom except the boundary raw, like this, then the reduced density matrix of this higher dimensional wave function generated by sequential circuit is nothing but a steady state of the repeated quantum channel. So this figure is known as the channel circuit duality, where the repeated quantum channel, if I keep all of the ancillary, correspond to a wave function in higher dimension, in one dimension and higher, generated by sequential circuit. And for this higher dimensional wave function, all of the qubits in the bulk correspond to the ancillary from a specific step. And then the boundary qubits correspond to a system of qubits. If I trace out all of the bulk qubits and only obtain the boundary reduced density matrix, this boundary reduced density matrix is nothing but a steady state of a repeated quantum channel. That says, indeed, I can visualize a steady state in a repeated quantum channel or Lindblad evolution from a pure wave function perspective from this holographic duality, such that any steady state in a repeated quantum channel should correspond to the boundary degree of freedom boundary reduced density matrix of a higher dimensional wave function that can be generated by sequential. In this process, the system qubits ended on the boundary. And in each layer, the bulk qubits correspond to the ancestor that feed you with a quantum channel in each step.
Do you insist on the locality on the left-hand side?
Yeah, good question. So from this sequential circuit, it seems that highly non-local because I have to entangle that first qubit with the end qubit. But it is still equivalent to the local sequential circuit from this diagram. So this is the usual diagrammatic representation of sequential circuit. Entangle the first ends with n plus 1. And for the usual sequential circuit, I can always add a swap gate, which doesn't change the locality. And then the process becomes entangle the first with 7, I exchange the first here, and then entangle the first with the third, and so forth. And these two are equivalent. So this doesn't seem to be local, but this is always equivalent to a sequential circuit that is locally generated, and the wave function too is very local. Okay, so this holographic viewpoint probably provides a potential shortcut for me to understand the steady state. Instead of solving the steady state of a repeated quantum channel, or just stare at the Lindblad master equation with constitutional hollow and figure out what is the steady state, maybe a shortcut I can do is I can just look at a wave function right on a Q state in higher dimension that can be generated by sequential circuit. And then what I need to do is just trace out everything about and only return the boundary reduced density matrix. This boundary reduced density matrix do correspond to a steady state of a repeated quantum channel. If I want to ask whether there are any interesting steady states, then what I need to figure out is, are there any interesting wave function in one dimension and higher that can be generated by sequential circuit? And I can just look at its boundary reduced density matrix. And in particular, the sequential circuit and the wave function have been explored thoroughly by people like Chen, Mike Hermey, and other Ukrainian people, as well as the tensor network community in terms of the ISO-TNX. So we already have a library of such kind of sequentially generated wave function to begin with, and probably for me to figure out interesting steady state. Okay, so the first part of the take-home message we need to remember is, in order to figure out a steady state for a d-dimensional repeated quantum channel, just to remember that such kind of steady state always allow you to have a holographic viewpoint such that such kind of steady state is nothing but the boundary reduced density matrix of a higher dimensional wave function that can be sequentially generated. And all of the information encoded in such kind of steady mixed state is nothing but the entanglement information of that higher dimensional wave function. Put the entanglement cut as the boundary. Okay, so this is the motivation. We can use channel circuit duality to visualize the steady state density matrix from holographic viewpoints. Now let me talk about SIG.
So does this circuit have to be sequential? So basically, it seems like you have this wonderful coupling. Where the system qubit is coupled to each transit qubit individually, and the front back there using the same unitary. So experimentally, we can think of this achieving the same circuit by applying the one-to-all like new gates simultaneously instead of doing it sequentially.
So you want to ask whether I can just have a highly non-local unitary that entangle the first bit with everything else.
Yeah, for example, like if I have system qubit in the center, and if I place Ancilla in a ring pattern, if I can realize the system to Ancilla coupling, and all one-to-all fashion, so can I just apply this Q in parallel without applying this sequentially by involving different soft gates?
Okay.
That's my question.
Yeah, so good question. So if you have such kind of sequential circuit settings, you can always combine all of these unitary in n step as a huge highly non-local unitary that entangle the first bit with everything else. However, if you just have a highly non-local unitary circuit that entangle the red bit with all of the other dark bit, there's no guarantee that that highly non-local unitary gate can be decomposed into such kind of sequential gate. So the forward is obvious, but the backward is not obvious, because if you have one to all type of coupling, in principle you can generate a wave function that going beyond the area law entanglement. But for sequential circuit, it can only generate area law entanglement state. And the other thing which is pretty important is that for all of the other qubits, in this process, they only entangle with the system. The first ancestor and the second ancestor, they shouldn't have any interactions. Otherwise, such kind of unitary circuit will not correspond to a repeated quantum. Because for repeated quantum channel, different ancestor degree of freedom do not talk to each other. Okay. So remember this fact about holographic duality. We will come back in just a moment. Then let me talk about symmetries, because I'm in that kind of fields. So, and I always feel that symmetry always play a pivotal role in modern quantum mechanics physics. When I say Q state, a wave function is symmetric, what I really mean is I apply a symmetry transformation, it's a unitary operator acting on the wave function, make it invariant apart from global phase shift. That is not important. And in mixed state, what we are dealing with is not just a Q state, we are dealing with a density matrix, which has cat and bra component. And hence, for the same symmetry, say Z2 symmetry, we actually have two types of symmetry to talk to. The first is defined as the strong symmetry, some literary term called exact symmetry, which means that the density matrix multiple, the symmetry transformation that only act on the cat space or only act on the bra space, still make the density matrix invariant up to some global phase shift. If I say a mixed state cascade symmetry, that says if I diagonal the density matrix to each of its eigenvector, they should carry the same formula. And the other notion of symmetry mixed state is known as the weak, or sometimes they call it average symmetry, where I have the symmetry transformation operator act on the cat and bra space simultaneously and make the density matrix. This is the usual symmetry we are familiar about, because when in quantum mechanics class, when we talk about an operator and is invariant under a symmetry transformation, this is what we exactly refer to as density matrix in the operator. If a density matrix have a weak symmetry, that means if I diagonal the density matrix and figure out all of its eigenvector, there should be an eigenstate of the symmetry charge, but a different eigenvector can have different symmetry charge. So go back to the standards. Strong symmetry or exact symmetry could correspond to a canonical ensemble in thermal equilibrium, where the system have energy exchange with the heat mass, but there is no charge exchange with the heat mass. So the whole system have a fixed number of charge. And average or weak symmetry can be viewed as something like a grand canonical ensemble where we have both energy exchange with the heat mass, and we also have charge fluctuations with the heat mass. So I can transfer a charge from the system to the heat mass and vice versa. Okay, so when we talk about symmetry, the first thing we will obtain from standard class is spontaneous symmetry breaking. Means for a lot of it, spontaneous symmetry. When we talk about spontaneous symmetry breaking, what we are really meaning is that a thermal density matrix, weak symmetry breaking. For example, we can think about a ferromagnetic case in one dimension or any dimension at the same temperature. They can have a ferromagnetic order where the density matrix of zero temperature thermal state is nothing but a convex sum. Either all of the spin pointing up or all of them pointing down. This density matrix, you have a weak C2 symmetry. And in the meantime, this density matrix also measures spontaneous C2 symmetry, which in my notation is a weak C2 symmetry breaking. And one way to plot the weak C2 symmetry breaking is we have to identify an operator that is charged under this C2 symmetry. We choose it to be the poly Z operators and measure its 2-point correlation function with charge spatial separation. Find this non-vanishing, that means we have a magnetization where the Z2 symmetry is broken spontaneously. So this is what we learned about symmetry breaking in thermal state under thermal. So this is something that we're most of you are pretty familiar about from undergrad, but there are two things I would like to point out. So for the usual spontaneous symmetry breaking, which is a weak symmetry breaking for a thermal state, we only need a partial information of the whole system, of the whole ensemble. So how do we prove spontaneous symmetry breaking? Suppose I have a d-dimensional ensemble, a bunch of Yizhi spins. I can either plot them through the usual correlation function. I just find a patch of A and C and measure their usual correlation function. Or I can measure the mutual information between the patch in A and C that are separate apart. If I have symmetry breaking, then they should carry long-range mutual information.
So does this density matrix that you've written down have a weak symmetry?
Yes, it has a weak symmetry, but it doesn't have strong symmetry.
But then, like, wouldn't I would think that weak to nothing SSB would mean that the state that you have is at the end is not symmetric?
Okay, so this is weak to nothing SSB. And what do you mean by symmetric is, if I just calculate a single charge operator on any side for this mixed state, it is 0. So the density matrix is still symmetric. However, what we have spontaneous symmetry breaking is that I can always identify a charge operator that is charged under Z2 symmetry, and they have long-range order spatially, which means I can create 2 charges to the system, even they are spatially separate without changing anything to the density matrix. Of course, if you pick up a specific ground state, like just to pick up this one, then it would repeat it explicitly, but the other one would restore it if you consider the whole ensemble at 0 temperature. And hence, no matter whether you are measuring the mutual information or the usual correlation function, I really don't need all of the information for the whole ensemble. Suppose I trace out harder degree of freedom, I just allow harder degree of freedom and only have the information of the rest of the trees. I can imagine that I just trace out a bunch of qubits in the middle. And for the remaining reduced density matrix, I can still tell whether I have a ferromagnetic trace or not, because all I need is measure 2-point correlation function or their mutual potential. I don't need the average in the inside. So this is about spontaneous symmetry breaking. Now we know it is weak symmetry breaking. But when we talk about mixed state, even for the same symmetry, say Z2, Yizhi symmetry, we can have a strong symmetry and we can have a weak symmetry. And obviously the weak symmetry is a subgroup of the strong symmetry. You have strong symmetry, you will have weak symmetry. So there could be a new scenario that I break the strong symmetry spontaneously, but the weak symmetry remains unbroken. So this scenario is what I call spontaneous strong weak symmetry. And what I will talk about is how do we understand the spontaneous symmetry and how do we measure them. So this topic has been explored pretty thoroughly in the past few years, driven by a lot of people into some degree. And let me just review some basic things from a simple example. So consider a Holland check. We first begin with our 1D state, which is initialized as a polarized state. Everything is polarized in the plus direction. So this is just a tensor product state of a 1D state chain. And I identify the strong symmetry, which is the product of X parity on the 1D chain. And I can introduce 2 types of quantum channels that respect the strong symmetry. I can either have a dephasing channel for the onside X, or I can have a dephasing channel for the ZZ operator on 2 nearest sides. And here P is something like a dephasing length or measurement noise can vary from 0 to 1 half. And if I apply both quantum channels repeatedly, these 2 quantum channels actually commute, so their order doesn't vary that much. I just apply the infinite amount of time beginning with such kind of initial polarized state. The steady state we obtain is pretty simple, and it is independent of the parameter P, the measurement rate here, provided P is non-zero. The steady state is actually an incoherent sum of different patterns that can be written in the X basis with a global constraint that the total X charge in the system is still even. And this density matrix can look pretty classical because it can be written as a classical sum of different unentangled states. Do realize strong to weak symmetry, which can be proved by the duality correlator. So first, it was actually initially proposed by Lindblad and Chuang per perimeter that the right prop of strong to weak symmetry should be defined through the similarity of the density matrix itself and another matrix which is acting a pair of charge on the cat and bra space simultaneously to them. And if we want to know the similarity between two types of matrices, what we need is just to measure the fidelity operators between two matrices. So to comment, first, what does it mean by we want to know the similarity between this the density matrix and a pair of charge operators on the bra space of them? This was partly motivated by how do we plot the usual spontaneous symmetry group and a weak symmetry group at 0 temperature. If I have a wave function, one of the ground state that is symmetric, what we can plot is just a plot their correlation function. Yizhi acting on the ground state. And this correlation function can also be viewed as the similarity of your symmetric ground state together with I create a pair of Z2 charge operator on site I and J acting on the ground state and check after creating a pair of charge their similarity with your original ground state. If they have the order of 1, that means creating a pair of charge, inserting a pair of charge to a ground state does not qualitatively change the ground state wave function. So we have Z2 charge condensate, and hence I expect the ground state should be symmetry free. And hence this is the same. The only difference is that now we are dealing with a density matrix, so a pair of charge should act on the cat and bra space simultaneously. And in addition, if this fidelity correlation that is non-vanishing only means that the strong symmetry is broken, because if I have a Zi operator acting on the cat and bra space simultaneously, such kind of operation is charged under strong to symmetry, but neutral under weak symmetry. If I also want to manifest that weak symmetry is still unbroken, I have to measure the usual correlation function of the density matrix and make sure that at least the decay superpolynomial with spatial separation. So this is what is already done by other pioneers for previous field. And what's unique about strong to weak symmetry from this abstract definition is about locality. When we detect whether a state have usual symmetry breaking weak symmetry, I don't need all of the information for the whole ensemble. Even I trace out a bunch of qubits for the remaining for freedom, I can still measure the correlation function to know whether I'm in a ferromagnetic space or not. But this is not the case for strong to weak symmetry. So for this density matrix, which manifests strong to weak symmetry break, suppose I trace out a bunch of qubits or even one single qubit and obtain the remaining density, reduced density matrix. That reduced density matrix with tracing out one qubit will just look like the identity operator, which is totally featureless. And in that sense, in order to detect or know whether I have strong to weak symmetry, I really need all of the information for the whole ensemble. If I just lost one piece of information, then for the remaining freedom, it is hard for me to say the original theory has strong to weak symmetry. This is pretty obvious from the fact that we need a fidelity correlator. If you just lost one qubit, then you cannot recover what's happening for that fidelity correlator. And later, it was manifest by people here like Yizhi that for strong to weak symmetry breaking, key feature is that it doesn't have any long-range mutual information, but it has a long-range conditional mutual information. If I tripartite the system into 3 areas, A, C, and intersect by some area of P with a width LB that can extend to the thermodynamic limit, the conditional mutual information in C over B should be non-vanishing. This was actually what Yizhi put from the past recoverability. And the third thing, which is unique in strong to weak symmetry breaking, is that if I consider a quantum check and repeat it infinite amount of times, or I consider a Lindblad matrix which still respect the strong symmetry, it's steady state will always have strong to weak symmetry breaking without any fine tuning, no matter what type of cross operator you choose or what type of jump operator you choose, strong symmetry should always be broken. This is a bit different from thermal equilibrium, where if I have a local Hamiltonian, 0 temperature phase, I can have a weak symmetry breaking phase like ferromagnetic phase, but I can also have a paramagnetic phase. But for repeated quantum check, strong to weak symmetry breaking is always expected. Okay, so after I introduce what is strong to weak symmetry breaking, let's go to the main thing. So previously I manifest that we can have a channel circuit duality to understand the steady state from a holographic view.
Sorry, quick question. I think I want to clarify the previous slides. You said strong to weak symmetry breaking is always expected. Is it possible to break it to nothing, or is it always?
Yes, yeah, there are two scenarios. One is strong only to break to weak, and the other is your weak symmetry is also broken, so it's strong to nothing broken, but you will have a strongly symmetric.
I see. So the repeated quantum channel, the steady state will always break the strong.
Yeah.
I see.
One more question. If the strong to weak symmetry breaking is very sensitive to having the global versus oneness, then can you really talk about in the thermodynamic limit where you only have access to local operators, which inevitably will miss at least one weakness?
Yes, and one signature of strong to weak symmetry breaking is either you prove the fidelity correlators or CMI, you always need all of repeated information. Because you cannot cross strong to weak symmetry from something that is just linear in matrix. Yeah, because for strong to weak symmetry breaking, your density matrix is still strongly symmetric, but the charge is not localized, it can strongly fluctuate from this side to the other side. If you trace out 1 degree of freedom, the remaining reduced density matrix would just become would only have symmetry.
But you use the fidelity correlator kind of just give a patch of the whole system and compute that.
So
Instead of taking you as a prudent thing to because if the left in the track that can be able to find the other. So that also gives you a signature of the.
So you mean if I just because this I and J probably only act on the patch with their spatial length, which is L. But the issue is for the remaining, you still need to do the matrix contractions. If you just trace out the remaining degree of freedom, then you will lost information. Like if I just take out one patch, the half length of the chain, and trace out the remaining, then the density matrix, at least for the previous study state, the half length reduced density matrix is just identity operator.
I see.
Once I have to multiple one, here it's a square root of density matrix, other square root of density matrix. If I have operators acting them, then I have operators acting them before contraction. If I don't have any operator acting them, then I have to have a cat and mouse space contractions. And this contraction is more like doing EPR projection into double picture. You have to have such type of information. Previously, I showed that any study set should correspond to a boundary reduced density matrix of a higher dimensional wave function, provided that the wave function can be generated by scale. And now I also know that for a 1D quantum channel, repeated quantum channel, with strong symmetry, we will always have our steady state with strong symmetry. And straightforward question is, how do we understand this phenomenon from a holographic viewpoint? Especially the density matrix that describes the kind of steady state with strong to weak symmetry should be some boundary degree of freedom, the boundary reduced density matrix of a wave function defined in higher dimension. And for strong to weak symmetry breaking work, we learn from other literature is they have three important components. First, you need a strong symmetry. And second, you have to prove it through the fidelity correlator. And finally, you should have a non-vanishing CMI. How do these three components correspond to in a higher dimensional wave function? In particular, because I need a strong symmetry of the reduced density matrix. This is already highly not true, because for a higher dimensional wave function, if it is just a Z2 symmetry, and I trace out positive graph and get a reduced density matrix, that reduced density matrix should only have weaks. And having a strong symmetry in your reduced density matrix already implies something highly true. So let's still go back to the kickoff example, but now I'm even simpler. I just make the dephasing channel to be the strongest dephasing channel where P is equal 1. So in this process, what I have is I have a system P, and I have some ancestor, which is some polarized state or an entanglement state. And I first have a quantum change, which That's the dephasing channel X, and then I encode with another quantum channel that gives me the ZZ dephasing channel. So after this one depth of quantum channel, I combine the two as one depth. The physical degree of freedom I have is for system, I have my input state, the hollow dot, the output state, the blue dot. And I also have two types of ancillary which will be traced out. One ancillary feed me with the X quantum channel, the other ancillary, which is the solid, feed me with the ZZ channel. For these type of degree of freedom, I can somehow write them as a wave function in the thin stripe limit, where the bottom part, the hollow dot, is my input qubits, the top blue is my output qubits, and the X quantum channel and the ZZ quantum channel live along the time direction link or live along the X direction link. So whenever I have a unitary gate that entangle the system and ancillary, I can always characterize in terms of a wave function in the thin stripe limit. This picture would be more pronounced if I just represent this unitary in terms of the matrix product state. So for this unitary that entangle the system with the ancillary, I have my input system qubits, output system qubits, and two types of ancillary. And such kind of unitary operator can always be mapped into an MPS tensor in the left canonical form, such that this is an MPS tensor that encodes with a one-dimensional Hilbert space. The left virtual leg corresponds to my input state of the 1D system. The right virtual leg corresponds to my output state. And the physical leg corresponds to my ancillary operator. For any unitary, you can write it in terms of an MPS tensor, and this is a left canonical piece. So for each depth of the quantum channel, I can represent it in terms of an MPS tensor, such that the virtual leg on the left and right are my input and output state of the quantum channel. And the physical leg degree of freedom corresponds to the ancillary, which need to be traced out eventually. Then, if I repeat this quantum channel, or repeat a sequential circuit, repeating them in time means my output state in the previous step eventually becomes my input state in the later step. And because these input and output state are nothing but my tensor's virtual leg, connecting them in time means first that I have to extend the MPS tensor along the extra dimension and doing the tensor contraction for their virtual leg. So eventually what I will get is I will get a wave function written in one dimension and higher. It could be an MPS wave function, but the matrix product state operator's dimension is just a one-dimensional Hilbert space, or we can also write them in terms of ISO-TNS. This is a wave function in one dimension and higher, where all of the qubits live on the physical bond are my ancillary qubits, which would need to be traced out eventually. And the left and right qubits that denote some type of boundary degree of freedom are actually my input state and output state of the quantum channel. So whenever I have a quantum channel, if I also retain the ancillary degree of freedom, that should correspond to a wave function written in higher dimension with open boundary condition plotted in this way, such that the bottom qubits are my input state, the very top edge are my output state, and everything else in the bulk are the ancillary qubits, which need to be traced out eventually. And that actually means that for the 1D quantum channel, we can have a space-time duality to do it into a 2D wave function, such that the repeated quantum channels time direction transform matrix or Euclidean's imaginary time evolution can be treated as the spatial transform matrix of a higher dimensional wave function written in the left canonical matrix. So in this picture, this is my input state, and this row and this row are actually my ancillary degree of freedom, which feed you with X quantum channel and ZZ quantum channel in the first step. And if I repeat it, I will have additional ancillaries from the second step and so forth, and eventually I'll have my outputs. So in this picture, the time evolution of a quantum channel, which is a non-unitary evolution, can be treated as a spatial transfer matrix of a higher dimensional wave function. And this helped me to understand the steady state, because when I talk about a quantum channel, as long as I know what are the cross operators and reason them out, spell them out explicitly, I can figure out what are the corresponding unitary sequential circuit. And then what I can do is just repeat this unitary and generate a higher dimensional wave function. Look at what's happening in the wave function and what's happening on the boundary. The boundary is my system of interest which should correspond to the steady state.
These tensors are all isometric.
Yes, because it's trace preserving and completely positive. For non-isometric, you can assume I have additional measurement like single measurement on the ancillary. Okay, so go back to the repeated quantum chart. It's not hard to figure out that the wave function that engendered in one dimension and higher, in 2 dimensions, is nothing but the ground state wave function of a stabilizer Tauric code on a square lattice. So for Tauric code wave function, we have 2 types of Hall stabilizer. One is the X vertex operator, which defines the local charge. The other is the AC operator, which defines the flux. And because it is written on open boundary conditions, for the top row, we also have a boundary stabilizer, which is the free product of Z, which tells you that I have a rough boundary with an E-condensed boundary. And for this wave function, which is nothing but a ground state wave function of the C2 Tauric code, everything else involved are the ancillary degree of freedom I should trace out eventually. And only the very top row is my system of interest. That's defined, its reduced density matrix defines the steady state. So for the 2D wave function, this is a Tauric code wave function where you have a rough boundary with E condensate. And E condensate means that under the boundary, I can create a pair of charge without causing in energy, and then let them re-annihilate in the bulk degree of freedom. This is what the E condensate of Tauric code is about. And its boundary degree of freedom also manifests strong to weak symmetry breaking. Because what does it mean by strong to weak symmetry breaking is my system and ancillary, although they are interacting with each other, there is no explicit charge transfer between them. However, the strong symmetry is eventually broken to weak symmetry spontaneously, means I can create a pair of charge and let them tunnel to the environment degree of freedom without costing any energy. And now the system degree of freedom is boundary, and the environment degree of freedom is nothing but qubits in the bulk. So such kind of charge tunnel between the Tauric code boundary to the bulk is indeed strong to weak symmetry. Okay, then let's recall what we know about topological order. For a 2D Z2 Tauric code with an E condensate, we can define a one-form symmetry charge for the E operator, such that I can drive a open string Wilson-line operators, which create a pair of charge in bulk and let them tunnel to the boundary. And because my boundary charge condensate, such kind of creating 2 charge at the boundary doesn't cost an energy. And if I measure such kind of Wilson-line operator for the 2D Tauric code ground state, it is of the order 1. And now, because I know that only the top row of qubits are system, everything is ancillary. If I trace out the ancillary, we'll see that the original Wilson-line operator only have a finite patch, only have touch 2 points here, and everything else is extended at the Z string in the bulk. If I barely trace it out, then the 2-point correlation function on the reduced density matrix should be short range of 0, because the other string extending to bulk can be even and odd, and once I trace them out, every result will be fuzzy. But if I consider something like duality or Renyi 2 correlator, we will find that this is non-vanishing, and such kind of non-vanishing V2 of duality correlator, which manifests that your boundary has strong to weak symmetry breaking, can be originated from the fact that your bulk wave function, the Tauric code wave function, has a non-vanishing expectation value for these Wilson-line operators. The other thing is for 2D Tauric code, apart from one-form symmetry for charge, we also have a one-form symmetry for flux, where I can draw a closed loop of X operator in the bulk, but I can also draw a closed loop X operator on the boundary along the non-control. This actually measures the harmonics of the global flux of the Tauric code on the cylinder. And because this string of X operator only acts on the very top row, if I trace out all of the remaining degree of freedom and only keep the top row as the reduced density matrix, the fact that my wave function is an eigenstate of this X string guarantee that your reduced density matrix should have strong symmetry. So the strong symmetry of the boundary reduced density matrix actually came from the fact that your boundary is a Tauric code wave function that has a one-form symmetry, and I can always draw such kind of a one-form symmetry string on the boundary. And in the previous tensor picture or sequential circuit picture, A strong symmetry indicates that the charge is conserved on the first row of qubits without charge transfer with the rest. And in the corresponding MPS tensor, that actually means that your MPS tensor has a tensor symmetry after Pauling operator on the virtual leg still makes the tensor invariant. So your ISO-TNS wave functions have some additional constraint on each tensor. Okay, so now it's clear for the strong to weak symmetry. Three components. First, we need a strong symmetry. Second, we have a non-vanishing fidelity correlator. Now we know that from the holographic viewpoint, the strong symmetry came from that one-form symmetry for the plus, which is one of the essential features for topological wave function. And then the fidelity correlator came from the fact that we have another one-form symmetry for the charge, and because we have a charge from that boundary, such kind of one-form symmetry can terminate as two points and at the boundary. And in addition, as I mentioned previously, the third feature that is essential for strong to weak symmetry breaking is the conditional mutual information. And for topological order, we know that one of the prominent property of topological wave function is topological entanglement entropy. So suppose I put a wave function on a hollow disk, and I take out a stripe and bipartize this stripe into three areas, A and C, that are connected by B. The topological entropy, at least in the continuum field theory, can be characterized by the conditional mutual information between ends over B. And in the continuum limit, this property is fantastic. And if I shrink this orange hollow layer into a smaller and a smaller stripe, such that it eventually only touch the inner boundary, now I can treat this wave function that outer boundary is my input state, and my inner boundary is my output state. And then this CMI is nothing but the CMI of the boundary reduced density matrix. And because that my original topological entanglement entropy have to be non-vanished, this also infers that your CMI for the boundary reduced density matrix that characterize strong to weak symmetry should have a non-vanished value. So from this picture, from this holographic picture, we have a pretty straightforward way to understand what is CMI about. It's because you can always holographically do it as the boundary of a higher dimensional wave function, having topological order, and this would guarantee that you should have a non-vanished CMI. Okay, so to summarize, turns out that for any studies in a repeated quantum channel, a long-time Lindblad equation, we can use a holographic picture to understand them as the boundary degree of freedom or boundary reduced density matrix of a higher dimensional wave function that can be sequentially generated. And in particular, for any strong to weak symmetry in a repeated quantum channel, it should correspond to the boundary degree of freedom for a higher dimensional topological order wave function that have charge condensate as the boundary. And in particular, the strong symmetry of the steady state is guaranteed by the fact that I have a one-form symmetry for the flux operator, which only acts on the boundary row. And the fidelity correlator is guaranteed by the fact that because I have a one-form symmetry for E and it can condense at the boundary, I can always create a pair of charges and let them tunnel into the bulk and re-annihilate. So this is something like a charge exchange between our system at the boundary and the end state in the bulk. And in this picture, the conditional mutual information has a pretty straightforward origin, which can be traced back to the topological entanglement entropy of a topological wave function. And then the time evolution of the repeated quantum channel corresponds to the transfer matrix, spatial transfer matrix of this topological wave function. So this is the whole picture. And in principle, although today I only illustrate one specific example, this can be generalized to any type of strong to weak symmetry breaking with discrete symmetries. For example, apart from the usual symmetry, we can also talk about uniform symmetry. And if I have a one-form strong to weak symmetry in two dimensions, it can be holographically due to some boundary reduced density matrix of a 3D wave function. And that 3D wave function should be the 3D color code or 3D Z2 gauge field, where I have M magnetic flux condensate boundary, so I can create a pair of magnetic flux loop operators and let them tunnel into the boundary from magnetic operators. And likewise, you have something more exotic like the fermionic one-form strong symmetry due from the boundary reduced density matrix of a fermionic color code. Okay, so let me wrap up. to the also not. So today what I do is I introduce a holographic viewpoint, which sometimes can be a shortcut to understand a steady state in a repeated quantum channel or Lindblad distribution. The statement is that any steady state should correspond to the boundary degree of freedom of a higher dimensional wave function generated by sequential circuit. So a possible shortcut is that we can just look into a higher dimensional wave function and look at its boundary. And today, when I introduce this example, I go from the boundary to I first consider 1D repeated quantum channel and extend it to a 2D wave function. But as a shortcut, we usually go from the other side, whether I can just pick up a higher dimensional wave function and look at its boundary reduced density matrix and see whether there's anything interesting without digging into the detail of the Lindblad distribution. However, not all of the wave function, their transfer matrix do correspond to a trace preserving and complete positive map like quantum channel. And in particular, the wave function we need to look into is called the isometric tensor network. So for a tensor network, we deal with local tensor, which have a virtual degree of freedom as a hollow and a solid dot, and a physical degree of freedom, which is this red dot. And for isometric tensor network, they can always be dual or extend into a local unitary gate, such that I entangle these qubits with the ancillary, which is shown as some trivial state. And the system qubits, their input state and output state correspond to some virtual leg and the other virtual leg in the other direction. And its ancillary qubits output state correspond to the physical. The unitary condition would automatically tell you that we will satisfy the isometry condition of the local tensor. And hence, if I repeat this quantum channel in time, this is equivalent as I'm doing tensor contractions about their virtual boundary. So once I repeated the quantum channel, and I still want to keep the ancillary degree of freedom, this is equivalent as I have a bunch of local tensors, and I do the tensor contraction and extend them in one dimension and higher. And for this isometric tensor network, their physical degree of freedom are considered to be traced out, and their virtual degree of freedom on the top and bottom correspond to one input and output state. And the spatial transfer matrix of ISO-TNS is actually the time evolution of a repeated quantum channel. So in this way, we can play with a geometry of isometric tensor. We can just have some relation to the tensor component and somehow write a phase transition for ISO-TNS wave function involved and also at the boundary. And corresponding question we can ask is what would happen if I tune the sequential unitary or tune some of the parameter in the repeated quantum channel to see whether there can be any phase transition in the steady state. And in addition, for the iso-TNS, I can somehow measure the correlation function between the top and bottom boundary. Such type of correlation function is indeed similar to the autocorrelator. As here, the bottom and top boundary are input and output state. So the spatial correlation is the time direction correlation of a sequentially generated wave function. So this is one of the output one can input. The other output, let me just briefly talk a little bit about is the generalized symmetry of strong to weak symmetry. Since I have shown that for any strong to weak symmetry group, it should be holographically due to the boundary of some higher dimensional wave function generated by sequential circuit, and it should exhibit topological order. For any type of topological order, although today I'm going to talk about protocol, there are three essential features. First, we need several type of higher forms. For example, for protocol, have a one-form symmetry for E and the other one-form symmetry for N. These two type of one-form symmetry involved have to prove the anomaly, which eventually guarantee that your wave function will have topological entanglement. And in the dual language, the steady state is nothing but the boundary reduced density. And the strong global symmetry can be traced back to one of the one-form symmetry involved. And this boundary reduced density matrix also have a weak one-form symmetry, which is essential for me to have a non-dimensional duality correlate. This weak one-form symmetry in one dimension can be traced back to the other one-form symmetry involved. And in above, these two type of one-form symmetry have two anomalies that engender topological entanglement and entropy. On the boundary, a strong zero-form symmetry and this weak one-form symmetry also have two entanglement, and their anomaly engender guarantee that you should have a non-vanishing conditional mutual information for the next state, which could be a signature of strong to weak symmetry break. Okay, so this is the other setup. It's telling me that all of the steady states with strong to weak symmetry understood from the generalized symmetries and their conditional mutual information actually came from the fact that two hoops anomaly between different kinds of symmetries. So I think I'm running out of time, and let me just go to the conclusion. Thank you.
So to get this like strong, like so let me say like you have like a strong zero form symmetry on the the reason why like you still have that after you've like traced out the bulk is if you have this one form symmetry now in the bulk. It seems like it would be enough just to have some kind of like subsystem symmetry, right? Like not necessarily like the formal, but just like every kind of layer has a symmetry. Why did something like that not appear? Like why did you always get these like deformable like one form symmetry rather than having like subsystem symmetry?
So the first comment is if you have a higher form symmetry, then you always have global symmetries and subsystems.
Yeah.
So it's the other thing is because if I want to plot a holographic picture, higher form symmetry is one way to get one reduce density matrix. But if you have a subsystem symmetry, like fractal, it is probably also have strong symmetry in the weak density. And why doesn't it happen? So for Z2 or Zn, any discrete symmetry doesn't happen because what we need is, apart from either form symmetry or subsystem symmetry, we also need a CMI. So we need to have some type of two-hooped analog. But for 2D with subsystem symmetry, line-like symmetries, there's only something like spontaneous subsystem symmetry breaking state, but there's not any state that can have something like fractal logical order in 2D. But from the CMI could tell us, so actually we know that I must have some type of wave function. I have topological entanglement and entropy. This is one reason for that. And the other thing is that this is just for Z2. For U1, I haven't checked, but at least for some type of repeated quantum channel that have strong U1 to strong to weak U1 symmetry break, the wave function do look like a sliding Lagrangian liquid when we have subsystem symmetry on each row. And there's no charge transfer between different, like only parallel charge different 2D sliding Lagrangian liquid, which is a calculus and a stable phase. So for U1 case, actually, it is a subsystem symmetric wave function, subsystem symmetry. Yeah, but for if you only have discrete subsystem symmetry in 2D, which is line-like symmetries, then the only thing we can have is in the bulk, we can only have spontaneous symmetry break.
But in high dimensions, so with discrete symmetries, you could presumably have subsystems.
Oh, we can, because actually one case we check is that the 3D is some type of fractal code, like Kleiner line code, which is somewhat an anisotropic version of the X cube. Its boundary reduced density matrix realized the 2D subsystem strong symmetry group.
I want to go back to the question, Joan's question that whether you can detect locally the strong weak SSB order. I thought the fidelity calculator does a job, right? For instance, you just consider to limit, say, the paramagnetic limit, where it's nothing broken, there it's short range. Just take a patch of the wave function instead of the whole wave function. And the other limit, and you set the local density matrix just identity, but then apparently, the pair charge injection on distance does nothing. So that fidelity 1, which is unreached.
I see. So you mean that identity operator, if you measure the fidelity correlator, it's obviously of the order 1, but
right.
In the meantime, that's a reduced density matrix only have weak symmetries. Because only if I have strong symmetry, it is meaningful to measure the fidelity operator, because the density matrix is strongly symmetric, but I can figure out some operator that is charged under strong symmetry that has long range.
That's true.
Yes, and it's not just ZJ acting on I for the fidelity, just the ZI itself acting on I. It's also non-vanishing. So it's not if you consider the connected correlator, it's the same because ZI acting on the density matrix, ZI itself, its fidelity with the original identity operator. It's also optimal.
But we had a similar issue when we found that Eurosymmetry breaking of the function of the pure wave function.
Yeah, for the wave function, then you have to fine choose the wave function. Like I have to choose a wave function itself is already symmetric, like the cat state. I cannot choose up state and down state. This is already explicit symmetry breaking. I have to choose a cat state that is symmetric, and then figure out that for that symmetric wave function, Zj, which created a pair of charge to the system, make the wave function invariant. Otherwise, then the connected correlator is Zi already give you a non-vanishing expectation value. Then I don't need to check Zi and Zj.
Then maybe
Somewhat related question is, you are emphasizing the fact that we have a strong symmetry state to start with, but the CMI criteria is applicable no matter what. You can surely forget about one degree of freedom. The CMI doesn't, non-vanishing of a CMI is preserved under that operation. I mean, that's precisely one of the Kittai-Pascal argument that you can deform the region, it doesn't change. So how should I reconcile the two? The CMI is signature, which is insensitive to losing one qubit, whereas your criteria to talk about the strong to weak symmetry breaking is very sensitive to that.
Yeah. So to be honest, I don't have a definite answer, but one thing I want to comment is that if you have strong to weak symmetry breaking for density matrix, then your CMI should be non-vanished. But if I just begin with a random density matrix, I don't even know whether it has strong symmetry. I don't even know what happened. It's pretty possible that you can fabricate some exotic density matrix that is not strong to weak symmetry breaking, but the CMI is still non-vanished. So the opposite does not care.
Is there any way you can design your quantum channel so that the bulk is not a topological but a double semi?
Yes, actually, for the double semi on the boundary reduced density matrix is 1 plus CZX. And that corresponds to another type of Z2 symmetry grid. We have two Z2 in one. One is the product X, and the other is the product of CZX, which is non-uncyclable. If I'm considering that a non-uncyclable Z2 symmetry, which would also be broken in steady state, then the bulk is the double semi, and your boundary have charge condensate.
Is there any way you can make the boundaries into some kind of gapless?
It's because that double semi on the flux is a semi on the charge is still a boson, so I just have charge condensate.
Right, yeah. In that case, yeah.
And the speaker. Lunch. Also a sign up sheet to read with the speaker as well. Very
Thank you.
Yeah.